Okay, so I'm going to get started with part 1 of my series, reviewing Organic Chemistry 1 for Organic Chemistry 2 students or students going into Organic Chemistry 2. So I'm going to start with this video is, this is part 1, the basics, part 1, video 1. Oh, let me get this. There we go. I don't know why it's, there we go. Part 1, video 1. And this is going to, part 1 is the basics of Organic Chemistry 1. So not mechanisms, not curved arrows, nothing like that yet. It's just going to be focused on learning about what you should have learned basically in the first 5 chapters of Organic Chemistry 1. And then video 1 is going to be all about bonding. Bonding and hybridization and intermolecular forces. So we're going to talk about what is a bond. And to do that, we'll have to talk about orbitals, and we'll have to talk about hybrid orbitals. I don't know why this is focusing in such a weird way when my hand is on it. It's because of this light. Let's see. No. Oh, sorry. Orbitals and hybrid orbitals. And that will lead us to hybridization. And then we'll dive deeper into what is bonds, and we'll talk about polarity and dipole moments. And then we'll talk about intermolecular forces. And so I'm going to do an overview of that in today's video, just to sort of get us started back with the basics. So I'll talk about what a bond is, and then how we can identify which hybridization the molecule is, because that comes up a lot in organic chemistry too. Okay, so let's start with what is a bond. So typically a bond is sharing of 2 electrons. And electrons exist in orbitals, which we know that those are like s orbitals, p orbitals, and that's the biggest ones that come into play in organic chemistry. So we have an s orbital and p orbitals, and there's 3 p orbitals. Because organic chemistry focuses on carbon, carbon has 4 electrons. So if you remember back to your building out your orbital theory in Organic Chemistry 1, carbon has 4 valence, or General Chemistry 1, sorry. Carbon has 4 valence electrons, so we would put 2 in the s orbital, which is the lowest energy, and 1 in the p, 1 in each of the p orbitals here and here, until we get to 4 electrons from carbon. And so really what these orbitals are, they're areas where electrons are likely to be. So this is what an s orbital looks like, and there's likely to be 2 electrons that are in this space, occupying this space. And that's calculated by math, basically. And then if you have any more than 2 electrons, like you have with boron and carbon and everything after that, then this theory, just having the s orbital, no longer works, and the places they're likely to be after that are the p orbitals. So, and those are kind of shaped in this weird, almost hourglass type shape. And there's 1 in the x direction, 1 in the y direction, and 1 sort of going into and out of the page in the z axis. So these areas where molecules are likely to be, where electrons are likely to be, exist around atoms. And then when atoms are going to bond together, there's an overlap of those 2 areas. So like if this is a hydrogen and this is a hydrogen, each hydrogen has 1 electron that it brings with it by itself. So when they bond together, they have 2 electrons, and those 2 electrons shared is what makes a covalent bond. So a covalent bond is made by the overlap of orbitals. And basically those overlap of orbitals, that's like an overlap of where 2 electrons are likely to be. So that's what we mean when we say 2 electrons are shared in a bond. Okay, so that is a review of what an orbital is and sort of what a bond is. But that's just a bond. This is like, for example, over two hydrogens, but it gets a little bit more complicated. Hang on. Sorry, I got a phone call, and I'm using my phone as my microphone. So, okay, so it gets a little bit more complicated, though, when we get into bonding of anything really other than hydrogen, because as you recall, I'm going to use two different colors here. I'll use blue and pink. So the s orbital of carbon has 2 electrons, typically, is what we say, and the p orbital of carbon, there's 3 p orbitals, and carbon has 4 electrons, so each of these p orbitals has 1. So if we were going to try to bond like that, I'll show you what that would look like. I have some little orbitals that I've cut out of paper. So let me get those ready, and then I'll kind of show you what I mean when I say it gets more complicated. Okay, so if we're looking at a carbon atom, I'm going to show you sort of the hybridization example. So say this is our s orbital. It's pink. It's kind of hard to see it. There's a little letter S there, but that's kind of hard to see. Okay, so this is our s orbital. And if you imagine on carbon, our s orbital is supposed to have 2 electrons in it, right? So you can see those 2 electrons in the s orbital, or you should be able to, if this isn't such a weird lighting. I don't really know what's happening here. Okay, well, that's not going to work for long term, but fine. So here's an s orbital with 2 electrons in it. And then moving out from that s orbital, then we have a p orbital. So you have this p orbital. You can see this p orbital completely covers the s orbital. And then here's p1, p2, p3 would be sort of coming in and out of the page, but I'll lay it flat so you can see. And then there's 2 orbitals here. So now we have 2 electrons that are in the s orbital that would be very difficult to get to form a bond. If we wanted to overlap an s orbital with maybe a hydrogen atom like this, that would be very difficult to get it to overlap to the s orbital because we literally can't even see the s orbital anymore. So all these electrons are sort of at different energy levels, and they're not really available for bonding, which is not good because carbon only has 4 electrons and it wants 8 electrons, according to the octet rule, to be happy. So this bonding actually doesn't happen using these s and p orbitals. What carbon does is it combines its 1s and 3p orbitals into 4sp3 hybrid orbitals. So it takes the 1s and 3p's, which are all blue, notice, blue and pink, combine to make purple. So that s and 3p orbitals combine to basically make 4 orbitals that arrange in a tetrahedral shape. So it's hard to show tetrahedral shapes on here because it's very 3D, but this kind of gives you the idea of now if these carbon atoms can have each of their 4 electrons at different, in each a hybrid orbital, each in one sp3 hybrid orbital, and then it would be much easier for this to overlap with, for example, the s orbital of a hydrogen, and therefore carbon is able to form bonds. I don't know what's up with this weird lighting, but so essentially when we have carbon combine its s and 3p orbitals, it's able to hybridize and overlap with other atoms' orbitals so that it can get the 8 electrons that it wants. Where it's very difficult to do that if hydrogen has 1s and 3p orbitals, all at different energy levels. It would make some weird lopsided bond. The s orbital isn't really even accessible because it's completely covered up by the p orbitals. It would just be really hard to do. So instead, we get these hybrid orbitals. So it's kind of a new way of thinking that you maybe haven't learned yet in general chemistry, but because we kind of want to give you the basics, but now you can kind of expand that and have a little bit of a deeper understanding of how bonding actually occurs. So that is sort of an overview of hybridization. And hybridization can take place where only two P's are involved and one S. So there's a variety of things that you can look at. Okay, so the idea that I just talked about here is if we have our blue and pink orbitals combine, so if we combine these three p orbitals and this one s orbital, what we end up getting is 4 sp3 hybrid orbitals. So each one of these is sp3 hybrid, so that carbon can participate in bonding by sharing electrons in an even way. So it can have 4 bonds that are made by overlapping these orbitals with other orbitals from other atoms, and they'll all be equal bonds, basically. It kind of gives symmetry to the molecule. And that's why carbon atoms have that sort of tetrahedral shape. So that they can form 4 bonds. So a carbon atom is able to, instead of having 3p orbitals, it has 3p orbitals and 1s. It has 4 sp3 hybrid orbitals, and those end up taking on this tetrahedral shape because that way each one gets 109.5 degrees between them, and that's the clearest way, or the only way, to arrange where each of these electron areas will get the most, they'll have the most space for those electrons, because electrons don't really like running into each other. And so each of these sp3 hybrid orbitals could then overlap with like the s orbital from a hydrogen, for example, to make bonds between carbon and hydrogen from an sp3 hybrid orbital and an s orbital. Or it can overlap with another sp3 orbital from another carbon atom. So this is what an sp3 hybrid carbon looks like. So each of these single bonds is made up by an sp3 hybrid orbital. Now, if perhaps we want a double bond to take place, double bonding is a little bit different because it only uses 3 different electron domains. So you only need 3 sigma bonds for a double bond. We get rid of one of those bonds, and there's only 3 bonds taking place now, 3 original bonds. 3 sigma bonds is what we call those. It's 3 electron domain areas. So because of that, we only need 1, 2, 3 hybrid orbitals. So in that case, instead of using 1s and 3p, we end up using 1s and 2p orbitals. So we take 1s and 2p orbitals, and we get sp2 hybrid molecules. And then if we have a carbon-carbon triple bond, there's only 2 sigma bonds, so we would only need 1s and 1p orbital. So that results in an sp hybrid molecule, or sp hybrid atom. So hopefully you can kind of see where I'm going with this, where if we have a carbon that has 4 bonds, that carbon will have a tetrahedral arrangement because it's made up of 4 sp3 hybrid orbitals. But if it only has 3 bonds, maybe to another carbon, sort of 3 bonds basically making up the backbone. These are all sp2 hybrid. And then this double bond right here would be made up of just a p orbital. So we took 2 of the p orbitals to make up the hybrid orbital, and there's 1 left over, and that makes up a double bond. And then if you have an sp3 hybrid orbital, say to another carbon, or sorry, an sp hybrid orbital, you have 1s, 1p, and then these 2 bonds right here are made up of these p orbitals left over. So that is sort of the theory behind why things hybridize. If that's confusing to you, that's fine. There is a quick and easy way to tell what the hybridization is of a molecule that you can use going into your organic chemistry class, and that's looking at sigma bonds versus pi bonds or electron domains. So if you look at sorry, I forgot we haven't gone over the condensed formula yet. So if you look at a carbon with 4 bonds to it, for 4 bonds, you need 4 molecular orbitals. Molecular orbitals would be made up of the hybridization of 1s and 1, 2, 3 p orbitals. So the way I think of it is we would need s, p1, p2, p3. So this is sp3 hybridized. If you have a carbon that is a part of double bonds, it's in a double bond scenario, we ignore the extra bond. This just all counts as 1. And we're looking at sigma bonds, if you remember the difference between sigma and pi. So if we're just only looking at the base bond, counting these 2 as 1, then we need 1 s orbital and 2 p orbitals. So we get an sp2 hybridized. And then if you have a carbon with triple bonds or a carbon with 2 bonds to carbon dioxide, we count each of these areas as 1. So we need 1 s and 1 p. So both of these would be sp hybridized. So that's a quick way to figure out hybridization. And then for sp2 hybrid orbitals, they're tetrahedral. So that explains the tetrahedral shape of carbon. These are trigonal planar, so they're flat. They look like this, just completely flat, not really 3D. And then if we were to do a carbon-carbon triple bond, so if I were to bond this one more time, it becomes linear because there's only 2 electron domains. So it looks like this. So that's an overview of hybridization, how you can find the hybrid orbital, find the hybridization of the carbon, and what shape it is. So that's sort of an overview of what is a bond, what are hybrid orbitals, and what is the hybridization of a molecule. Now, we haven't talked yet about polarity and dipole moments. In all of these examples, we're sort of assuming that between 2 carbons, for example, the bond is made up of 2 electrons in these overlapping orbitals that are evenly shared. But we know that's not always the case from Gen Chem, where if you have a carbon and a fluorine, for example, the fluorine is much more electronegative, meaning it wants that electron density a lot more than the carbon does. So the fluorine is going to be pulling, like a game of tug-of-war, the electrons towards it. So instead of the electrons sort of be equally shared, they're going to be clustered towards the fluorine, meaning that this fluorine is partially negative. So that little sign, I think that's a lowercase delta in Greek or something. This means this is partially negative, and this means this is partially positive because it's losing some electrons. So that makes this overall molecule not be equally shared electron density, but there's a lot more electron density here and a lot less electron density on the other side. So this would be a nonpolar bond, and this would be a polar bond. So we can have different types of bonds. Either electrons equally shared in nonpolar bonds, or polar bonds where one side of the bond is really negative and the other side is really positive. And the same thing can apply to molecules. So for example, in a water molecule, we have 2 polar bonds. So there's a stronger area of electron density around this oxygen, and then a lot less electron density around these hydrogens. So this part of the oxygen molecule is negative, and each of these hydrogens are positive. So, so we have polar bonds, but we also have polar molecules. And that matters because the way two molecules interact have to do with their polarity. So this brings us into intermolecular forces. Intermolecular forces are sort of the way two molecules interact. So you have something that's nonpolar, so we'll say like carbon-carbon, the electron density is equally shared around here. When that comes close to another nonpolar molecule, these electrons will repel each other. And so what actually happens is they start to draw near each other. I kind of call this the bridesmaid effect. As they draw near each other, the electrons will gather on one side of one, and they'll repel to the other side of the other molecule. So these are positive, where there's no electrons, and negative on the other side. And so these are temporarily drawn together. And this is called London dispersion forces. And the reason I call this a bridesmaid effect is if you've ever been in a wedding, if you're part of the wedding party, I have been on a lot of bridesmaids parties. There's this bond that exists just because of proximity, because we're all in this bridesmaid thing together. So while we're all near each other, we spend a lot of time together. We're all like there for the bride, on team bride, so we connect in that time period. But then as soon as we're not near each other anymore, we are no longer bonded. We're no longer drawn to one another. So London dispersion forces happen when two molecules come near each other, they interact with one another. Now, dipole-dipole happens when, say, we have a carbon-oxygen bond, and there's that polarity present. So one side has a lot more electron density, and the other side has a lot less. That's like permanently built in, where the side is partially positive and that side is partially negative. When that comes into contact with other molecules that have the same thing, because this is a permanent pole that's built in, is a much stronger attraction. So these are dipole-dipole interactions. And this matters because the oxygen here is drawn to the positive part of this carbon, right? And as we get deeper into organic chemistry, you'll see that when there's an area with more electron density, that's going to be drawn to areas with less electron density. So the reason reactions happen is because of these intermolecular forces drawing molecules together. So that's why we spend most time talking about it. But then there's, of course, hydrogen bonds, which are what I like to call super dipoles. So you have a hydrogen bonded to an oxygen, like we do in water. The electron density is so strong around the oxygen and so small around the water. There's a really strong difference that if you bring two of these together, they're bonded together so strongly by that positive and negative attraction there that it is almost like a bond. It's not quite a bond, but it's so much stronger than other intermolecular forces that we call that hydrogen bonding. It's a better name, I think, would be like super dipole-dipole. It's a very strong dipole moment. So we call that super dipole-dipole, but it's not. That's what I call it. But technically, hydrogen bonding is what its name is, even though it's not really a bond. So it's a bad name. And this happens when hydrogen is bonded to the three most electronegative atoms: fluorine, oxygen, and nitrogen. Okay, so that is an overview of what a bond is, orbitals, hybridization, polarity, dipole moments, and intermolecular forces. So I hope that was helpful for you as an intro to Organic Chemistry 1, or an intro of review, I guess, for Organic Chemistry 1. And if you have any questions, please let me know. And if you want to do practice problems on this, I have chapter 1 practice problems that relate very closely to this, and you can just follow along in the video and do them. All right, well, good luck studying.